Hello, our dear viewers. Welcome again to our new edition of the Hope Chemist series. Today we are putting our emphasis on the Witting reaction, which is a reaction which was discovered by a scientist known as Georg Witting in 1979. In the introduction, the Witting reaction is an important and useful method for the synthesis of alkenes, which involves the treatment of aldehydes and ketones with alkylidine, triphosphoran, which may simply know as phosphorane. We have an example here of such a reaction. This first one, which is having triphenyl, phosphorus, and then a double bond burden to CH2, is what we know as a phosphorane. And as long as we are reacting it with a carbonyl carbon, we have an exchange of groups. The oxygen is exchanged to phosphorus, and the CH2 on the phosphorane is exchanged to the carbonyl carbon, so that we come up with a carbon to carbon double bond. That's why we say that it is an easy way or another alternative of the synthesis of alkenes, and in this case mainly terminal alkenes. So we look at the preparation of the Witting reagent. The Witting reagent is prepared by treating a trialkyl or a triaryl phosphine with an alkyl halide in presence of an ether solution as our solvent. So the resulting phosphonium salt is treated with a strong base, and in such bases we have butyl lithium, sodium amine, sodium hydride, or maybe sodium ethoxide, etc., as long as it is a stronger base, and which one removes the halo acid and gives us the methyl triphenyl phosphorane. For example, as you can see here, this is a scheme of how we can prepare our catalyst, our Witting reagent, which is very key in the Witting reaction. We can see we are having triphenyl phosphorus, we are having the methyl bromide. We form this intermediate, which is treated by the base to form our compound, which is undergoing resonance. We can see this resonance in this next step. We also know it as a halide. So compounds which have adjacent positive and negative charges on the same compound, we also know them as halides. So our triphenyl phosphoranes can also take on the name of a halide because of the resonance which exists. So in the halide, we can consider our carbon ion, which is negatively charged, and it is stabilized by the adjacent phosphonium cation, as we can see in this case here. So our catalyst or our reagent, Witting reagent, exists in either of these two forms, either with the positive charges already permanent or with a double bond between phosphorus and carbon. Moving forward, we are going to look at the mechanism. This mechanism, the negative charge on the carbon of the halide or our Witting reagent attacks the carbon atom of the carbonyl compound, since we already know that it is already electron deficient due to the presence of oxygen, which is more electronegative. So a negative charge is created on the oxygen atom, and then this compound or this intermediate is known as the betaine intermediate. Then the negative or excess oxygen atoms attacks the phosphorus, and we form a four-membered transition state which undergoes rearrangement with breaking of bonds to form the phosphoxide, the triphenyl phosphorus oxide, and our alkene, as we can see. So this is the major, or these are the main steps which are involved in our mechanism. Next, we look at the examples which involve or where the Witting reaction can be applied. For example, the Witting reagent can be treated with a ketene to form these compounds. We can also treat it with isocyanate, we can also treat it with the nitroso compound, or even imines. So it is not only strict to carbonyl compounds, but also ketenes, isocyanate, nitroso compounds, and imines can be treated with the Witting reagent, and the respective compounds are formed, and we be able to get the products. But the main cause is that we are forming a carbon, mainly a carbon to carbon double bond, or an alkene is generated. So some of the applications, we have the formation of exocyclic methylene group. As we can see, we have cyclohexanone. When we treat it with that, we form an exocyclic carbon to carbon bond. Exocyclic means that the double bond is on the outside, not within the cycle. So as you can see here, we are forming a double bond outside the cycle of the cyclohexane. Then we also look at the preparation of vitamin A. This is a complex compound which may not be easily synthesized, but with the help of the Witting reagent, we can be able to treat this first compound, our aldehyde compound, with a reagent which has been prepared to form a Witting reagent. And when we reduce that, the ester side, we come up with our compound known as vitamin A. Moving forward, some other examples or applications is the synthesis of vinyl halides. For example, if we have benzaldehyde reacting it with this reagent, this reagent for the Witting reagent can be prepared when triphenyl phosphane is treated with a chlorocarbene. So when you treat triphenyl phosphane, we treat it with a fluorocarbene, we form this type of Witting reagent which helps us in preparation of vinyl halides. So vinyl halides are the one which have the halogen compound directly attached to the carbon which is on the double bond. As we can see, this is another example. It is also exocyclic vinyl chloride. Moving forward, we look at synthesis of ethers, whereby also one of the sides which is having or which is going to form that group is connected to an ether, as we can see in this example. So with very many examples, as long as we have the carbon to oxygen double bond, we can easily treat those compounds with the Witting reagents and come up with the desired products. In conclusion, we are reminding you to subscribe, like, and comment. But however, before we close up this series, the Witting reaction is useful in various synthetic applications, mainly for natural products which are very difficult to prepare, as we have seen for the vitamin A. And also something to note is that if we are treating the phosphonium salt and the one which is involved is optically active, the reaction does not change the configuration of that salt. So it means if we had an optically active element, also our product becomes optically active. So the Witting reaction is very important because of that retention in configuration. For example, if the compound was deflecting our plane polarized light to the right, it still gives us a product which has the same abilities. So thank you for listening and watching.